A many-sided shape is called a polygon. These will always have straight sides, or flat sides if you want to think of it like that, never curved sides. So this is called a polygon. Each side of the polygon is called a line segment. And line segments, they meet at a point called a vertex, just like we showed in a triangle. So this is called a line segment. We use capital letters to designate the names of vertices. They're typically the most important part of a polygon. So for instance, A is this vertex here, B is this vertex here, and the line segment between them we designate as AB with a little line above it. If we draw a line segment between two vertices that are not adjacent to each other, for instance, let's say this one here, this line here, this line segment here, this is called a diagonal of the polynomial. This typically makes more sense when looking at four-sided figures. For instance, like this rectangle here, if I draw a line through there, this is clearly diagonally across the rectangle. But in general, any line segment connecting two non-adjacent vertices. So adjacent vertices just means like if this is A, this is B, C and D. A and B are adjacent, A and C are adjacent, A and D are not adjacent because they're across the polynomial. It should be noted that line segments are not indefinite in length. A line, by definition, is something that continues on indefinitely. It continues on forever. We write that. We always draw lines with these arrows here. That's to designate they continue indefinitely. Line segments is just a line like that. It has a starting and stopping point. Now, four-sided polygons are called quadrilaterals, quad meaning four. If two of the sides are parallel and the other two are not parallel, that typically is designated as a trapezoid. So for instance, this would be a trapezoid. These two line segments, let's say, let me name the vertices here as A, B, C, and D. Line segment AB and line segment CD are parallel. That's typically written as line segment AB are parallel to CD. And then AC, line segments AC and BD, these do not share parallel. They're non-parallel. They're just kind of whatever else you want. So another example of a trapezoid could be something like this. That's a trapezoid. But this is not a trapezoid. That's because opposite sides are parallel. These two are parallel, and these two are parallel. This is called a parallelogram. That's where two opposite sides are parallel of a four-sided figure. We also need that opposite sides be equal in length. That's designated with these little bars here. So the two bars and the two bars are equal, and the one bars are equal as well. So let's name this. Let's use like J, K, L, and M. J and K, the line segment JK is congruent to the line segment LM. The same thing is true about KL being congruent to JM. That's what a parallelogram's features are. If all of the sides are equal, the parallelogram looks more like a kind of shifted square. This is called a rhombus. I should write trapezoid here. Parallelogram. And this right here is called a rhombus. That's where all the sides are equal and opposite sides are parallel. Of course, if a parallelogram has right angles, so if we kind of align the sides up of a parallelogram, this is called a rectangle. Opposite sides are equal and opposite sides are parallel and they meet at right angles. And finally, a rhombus, if it's aligned completely, we have 90 degrees all the way around and all sides are equal. This is a square. So if you want, you can kind of break this thing down. Like this is polygons. We can't have a two-sided polygon because that would be two-dimensional. We can have a three-sided. Three-sided gives you triangles and the breakdown of triangles. If we have four-sided, that's what we're looking at here. We kind of have two separate things. We have a trapezoid. Well, we have three, I guess. Trapezoid, parallelogram, or just kind of like you can kind of use the word scaling, but that's typically used for triangles. It's just like there's no special relationship, so I'll just say not special. Trapezoid can be further broken down, but it's not really used in very many things. Parallelogram or rhombus. And a rectangle. Rectangles have 90-degree angles on the sides, and a rhombus has all equal sides. And then both of them come together to give you the square. And of course, you have five-sided shape, and you can have what's called regular polygons and non-regular polygons and things like that. We're not going to get into that. We're really just concerning ourselves with quadrilaterals and then polygons kind of ideas in general. Now, two of the most useful pieces of information about polygons, besides the classification of them, which tells you a lot of other properties, but the two most important pieces of information is area and perimeter. Area and perimeter. So the perimeter is really just the distance around the outside of a polygon. So I could have any kind of shaped polygon here. And let's say I have, I don't know, 2, 3, 2.5, 2, 1, 1.3, 4, and 0.5. The perimeter is just add these all up together. And that's the perimeter. That's what it is. For the for all the shapes, just add them up. The area, however, is asking the question: how many 1x1 square units? That could be either inches, feet, centimeters, meters. Whatever a unit of distance you want. How many square 1x1 unit boxes fit in the polygon? That's really what we're asking with area. For squares and rectangles, it's quite simple. That's because they are, by definition, squares. And so you're just trying to figure out how many unit squares fit in them. And so that tends to be very simple for them. You just keep going all out. The same thing is true for rectangles. When you deal with the rhombus and the parallelogram, it's a little different because this is like it's angled, right? So you still want to know how many square things are in there, but now we have this non-squared side, and so we can't quite fit anything in there. So the area with the square and rectangle is quite simply base times height. base times height. With the parallelogram and the rhombus, right, you don't just have this base measurement here and this it being the height. No, you don't take the base times height. This is actually more like a width, but you can find the height of this by going straight down. This is the height. And if I were to take a parallelogram like this, if I were to take this thing, cut right there with like a knife, and then move it right here, then what I get is a rectangle. And so as long as I multiply the base being the base measurement here being this measurement, and this measurement here being the height, then I can do base times height. This measurement here, this is more like a width measurement, or kind of it's kind of how tall it is, but it's not quite the height. That's not using the area measurement. It's base times height. The same thing is true for the rhombus. Base times height. Now the trapezoid is a little different. It requires a little bit more work. That's because there's no fancy technique that we did here for the parallelogram and rhombus. This actually has a nice formula that you can use. We're still considering the height being this distance here. But now what we're doing is we're taking the average of the bases, and those bases being the base 1 and base 2. Those are the parallel sides. They're always the parallel sides. And what we're doing is we're kind of saying, well, this thing is actually the same thing as a rectangle with, let's say the average is going to be about here. So it's going to be like this. And the average between those two bases is about here. So it's going to be like a rectangle with the exact same height. So this is base 1 plus base 2 over 2. And this is the height. So we're making a square out of it. We're doing this kind of, we're kind of cutting it off there and flipping it over, cutting off there and flipping it over. But I guess it's actually a lot like the same as a parallelogram, but it just takes a little bit more work because of the non-parallel sides. Let's just do some problems with these, and I'll show you how we do in practice, right? The perimeter and area of these figures here, we have an 8x6 rectangle. 8 is typically given to be the length, or I should say the longer side is typically given to be the length. I'm gonna write that as an 8 meter and a 6 meter rectangle. Now to find the perimeter, very simply, you just add up all of the side measurements. So we have a 6 meter plus an 8 meter. That's this one and this one. Now this one here is also 6 meters. And finally, this one here is 8 meters. That's because opposite sides are equal. 6 plus 8 plus 6 plus 8, that's going to be 14 plus 14, which is 28 meters, which is the perimeter. The area is just base times height for a rectangle. Base times height, you can also think of it as length times width, same thing. Base times height is 6 times 8, which is 48. And this is going to be the unit that you're using, meters squared. It's square meters. That's what an area measurement is. Okay, the next one says a square with side length 7 feet. You only need one measurement here because a square has every side the exact same measurement and unit. So the perimeter, well, that's quite easy. It's just going to be 4 times 7. It's just 7 plus 7 plus 7 plus 7, which is 4 times 7, which is also 28 feet. The area, I should say this was the area. The area is going to be a base times height again, 7 times 7, which is 49 feet squared. You'll notice that both of these have the same perimeter, 28 and 28, but the square actually has a larger area. It's taking it's the best use of space. It's the most space you can get on the inside. All right, let's look at the parallelogram of 12 kilometer 12 kilometer by 6 kilometer parallelogram. That's pretty huge, with a 4 kilometer height. So let me draw that. We have 12 kilometer by 6 kilometer with a 4 kilometer height. All right, the perimeter, quite simply, right? We just add up all the sides. 6 plus 12 plus 6 plus 12. 6 plus 6 is 12. 12 plus 12 plus 12 is going to be 36 kilometers. The area is base times height. Now, this is the base, and this is the height. So we're going to go 12 times 4. 12 times 4 is 48, and it'll be kilometers squared. Next one says a trapezoid with base lengths 10 and 15 and side lengths 7 and 8 with a height of 6. So 10 and 15. This is going to be the 15 one. Let's see. I think it's going to look something like this. 10. One side was longer than the other side. It was 8, 7 with a height of 6. Let me make sure of that. 10, 15, these are all in millimeters. 7 millimeter, 8 millimeter, and a height of 6 millimeters. Very good. Okay. The perimeter is going to be 15 plus 7 plus 10 plus 8. These are all in millimeters. 15 plus 7 is 22, plus 10 is 32, plus 8 is 40. 40 millimeters. Now the area, I'll do down here, is base 1 plus base 2 over 2 times the height. Base 1 and base 2 are the parallel sides. The height is a straight vertical distance. So we have 10 plus 15. Well, it'd be 15 plus 10, right? The way I wrote it out. Over 2 times 6. That's going to give us 25 over 2 times 6, which 25 over 2 is 12.5 times 6, which equals, let's see, 75. This is going to be in millimeters squared. This is a simple problem, but it's kind of an interesting one to think about because it's a property of quadrilaterals. What is the sum of the angles of a quadrilateral? Now this is saying that every single quadrilateral, no matter which it is, a parallelogram, a rhombus, a trapezoid, a square, a rectangle, or none of the above, every single one of them has the exact same sum of the angles. That's because it's just saying a quadrilateral being a four-sided shape. So this is quite easy to find out because you can just choose the easiest one, which is a square. All the interior all the angles in a square are 90 degrees, and there's 4 of them. So 4 times 90 degrees is 360 degrees. So if you actually were to cut these all up, right? Cut them all up and rearrange them, what you'll see is that you can rearrange them to be like this. And that is a full circle. So that's why it's 360 degrees. Now this can be done no matter the quadrilateral. This can be done with rectangles. That one's easy to see because it's the same thing as the square pretty much. With parallelograms, it can be done, and rhombus, of course. Right? This and this. I'm showing you a double bars there to show that those two are equal and these two are equal. You can cut this up and it'll look something like this. I'm drawing the wrong way. And you do it this way and then like this. There we go. That makes more sense. So this is the double-sided. So let me use a different color here. So these are the long angles. And these are the short angles. And you see we have a circle again, all the way around. That's 360 degrees. A trapezoid will also have the same property, right? Let's just make a weird trapezoid like this. And we have these two angles here. Those equal to 180 degrees if we add them up. And these two angles here equal to 180 degrees if we add them up. What you'll see is that you get something like let's see, we have, it's kind of hard to draw it out, but what you can do is you can cut it up, right, and move this one down here, and you see that we have a straight line. The same thing is true on this side, right? If you move this one up here, we have a straight angle, and we can adjust those two straight angles together to give us 360 degrees. And that works for every quadrilateral, even if it's some wonky shape, you know. It's hard to draw a quadrilateral that's not one of the special ones because you're so used to drawing those. But this even has the same property that all of the angles on the inside are going to equal 360 degrees if you add them up. All right, here we have how many square feet of wood is needed to build the cabinet. I think we're only considering the outside and not like the inside shelves and that kind of thing. I think we'll also consider the front of it as just a flat measurement, like the actual door of the cabinet. So how many sides are there on a cabinet? Well, if you think about it, there's going to be 6 sides, right? We have this top side here, this side that's facing us, the door. Then you have the back of it, the underside of it, and the left side of it. So there's 6 sides total that we have to consider. And we can use these measurements to find all of them. So each side is going to be important to all we really have to do is find the area of each side, because then that tells us how many square feet is needed for that side, and add all those sides up. That's how much square feet of wood we will need. So the top here and the bottom are actually the exact same shape. That's because we are making a square, well, it's a rectangular cabinet, but we're making all of the sides, all the angles 90 degrees. So it's going to be a perfect rectangle on top and bottom. They're going to be equal. So what's the top measurement? The top measurement is 1 foot 9 inches. We really want a single measurement here. So I'm going to change this to just feet. 9 inches. And write that over 1 as 12 inches to 1 foot. So those units cancel, and we get 9/12 of a foot, which is 3/4 or 0.75 feet. So we have 1 and 9 inches is 1.75 feet. 2 1/3, 3 inches over 1. This is the same thing as just saying 3 inches, like this, is 1 foot over 12 inches. We get 3 over 12 inches, which is 1/4, which is 0.25. This is 2.25 feet. And 3 feet 6 inches. 6 inches is half of a foot, so I'm just going to write 3.5 feet. Okay, now I can calculate the side measurements. So the top and the bottom are both 1.75 inches by 2.25 inches. So the area of this, that's all we're trying to find here, is the square feet of wood. That's area. Area is going to be 1.75 times 2.25, which equals 3.9375. And there's 2 of them, so we need to multiply that by 2. That gives me 7.875 square feet. Okay, so the top and bottoms are done. Now we need let's do the front and the back. The front you see here. Let me make this a little bit easier to see. This was 3.5 feet. The front here has a 3.5 feet by a 2.3 feet. That's because this is 2.25, I meant to say. Sorry. This is 2.25. This is going to be 1.75, 1.75. This is 3.5. You can see how all of the measurements around one side of the thing are the same. That's because it's actually called a prism, a three-dimensional figure, but we're looking only at the flat sides, which are making a two-dimensional figure, which is a quadrilateral, namely a rectangle. Okay, the front and the back are both the same. They're going to be tall, like this. It's 3.5, and it was by 2.25. So the area equals base times height gives me 7.875, and we have two of them. Gives me 15.75 feet squared. That's for the front and the back. Now all we have left is the sides, and the sides are going to be 3.5 by 1.75. A little bit thinner. So the area equals 3.5 times 1.75, which equals 6.125. And we once again have two of them. So times 2 gives me 12.25 feet squared. So adding up all of our side measurements, we need 7.875 plus 15.75 plus 12.25. If we add all those up, we get, let's see, 875 plus 5, 12.25. I'm getting 35.875 square feet of wood. Probably you say 36 square feet. Okay, this is an interesting problem. We have a roll of material. It's 46.5 centimeters wide. So you can think of like a roll of material, right? This is like a rolled up material. And when you look at it, head on, it looks like a cylinder, but it's a rectangle. And we know that this measurement here is 46.5 centimeters wide. Now we're asking how much do we have to unroll, right? We're gonna just unroll it to some measurement here. We're asking how much do we have to unroll if this is going to be the width measurement. This is 46.5 centimeters. How much do we have to unroll so that we get a total of 1.2, so we need an area of 1.20 square meters, or meters squared. Now what's important to note, as you can see with this careful, it says the numbers are not expressed in compatible units. We want meters squared. We know centimeters wide. So we need to first change centimeters to meters, and then we need to round to the nearest centimeter, which is also a little weird. So we actually want to maybe convert back, maybe. Let's first convert to meters. So 46.5 centimeters equals, so in 1 meter, in 1 meter, we have 100 centimeters. So we get 0.465 meters. Okay, we want an area of 1.2 meters. Well, that's quite simple. This is just a rectangle. This is a rectangle that we're going to cut. Right, we're just going to cut it right here and we get a rectangle. And we're asking, how much do we have to unroll it? How much do we need? Well, the area of a rectangle is just base times height, which is going to be x times 0.465 meters. And we want this to be equal to 1.20 meters squared. Well, we don't need the units in there. To find x, all we have to do is divide by 0.465. That gives us 1.2 divided by 0.465 gives us 2.580645. I'm going to leave a bunch of units because we have to go back to centimeters. This right here is in meters. We need to round to the nearest centimeter. You could do that here. Centimeter would be this spot right there. But I'm just going to show you that by going backwards. 2.580645 meters. 1 meter is 100 centimeters. So we get 258,064. I got a decimal point. Centimeters, and we're rounding to the nearest centimeter, which is right here. We look at this point. Is it 5 or greater? No, it is not. So we drop the decimal part. We get 258 centimeters long. That's how much material we want to roll out to get the proper area measurement of 1.2 square meters. All right, last one. We have a playground basketball court is 94 feet long and 46 feet wide. I like to draw pictures whenever possible. It tends to help out in the long run when you get used to visualizing what they're talking about. So this court is being resurfaced at a cost of $3.25 $3.25 per square foot. What is the resurfacing cost? Well, if it's in dollars per square feet, then we need to know what the square footage of the court is. In other words, what is the area in square feet? Well, we know what the base and the height are, right? This is just a rectangular court, so the area of this is going to be 46 times 94, which is 4,324 square feet. And if we know that the cost is $3.25 per each square foot, and we have 4,324 square feet, then the total cost is going to equal 4,324 square feet times $3.25 per square foot. 3.25. That gives us a grand total of $14,053.